Hey everybody, we're back again to do 3.1.2. We're going to do questions 24, 25, 26, and 27. I'm going to show you those. So here we go. Sorry, it lags. Okay, so this is just a reminder again. In the previous lessons, you named several algebraic methods to solve different kinds of equations and systems. I think you did some homework on systems. You're going to learn to solve more equations focusing on how graphing can help you solve them to check solutions. So this is the first question right here. It's about solving this equation. If you have a square root of 2x plus 3 equaling x. One way we can do this is with algebra, so that's what's going to happen over here. The only way to undo a square root is to square both sides. So if we do that, this side's going to square, that's squared. So this becomes 2x plus 3 equals x squared. It's got a square, so ideally we want to get everything on one side equal to 0 to try to solve. Maybe we can factor this quadratic. Since my square is on the right and positive, I'm going to move everything to the right. So that would make this 0 equals x squared minus 2x plus 3. This one factors nicely. It is x minus 3 times x plus 1. And if that still equals 0, it means we can think of our solutions as x is 3 or x is negative 1. Because 3 minus 3 is nothing. Nothing times who cares is always 0. Same thing on the other side. Negative 1 would be what would plug in. How many solutions did we come up with algebra? 2. All right. Now we've got to think about this. We're going to think about this another way. So we've got a friend here, Miranda, and Miranda's going to split this equation into 2. She's going to do y equals the square root of 2x plus 3 and y equals x. Quick little check. How many solutions does the square y equals the square root of 2x plus 3 have? Infinitely many. There's an infinite combination of xy points that are going to make that true. Same with the next one. Both have infinitely many solutions. As a quick reminder, there is a PDF of this in the slide deck if you want to have this document to write on as well. So here we go. Miranda says I'm going to graph both of them. And she's going to check the solutions from part A. So she's going to see if these solutions right here are what we get when we graph them both. I have already typed them into Desmos. We could graph them by hand, but here we go as well. We have the graph of the square root of 2x plus 3 and y equals x. So here we go. I'm going to, oh wait, I can split screen this, right? Sorry, this might be, let's see if it's gonna work. Ooh, yay. I don't know if I know how to do this well. Sorry guys. Maybe that's not how we get the whole thing on here. Okay, well, I always can't remember how to do that. How do I drag it? Sorry that you're watching this. I guess, never mind. Fun. Okay, well. Oh, there it is. Okay, sweet. And I'm gonna try to get rid of this, but here's this side, right? So actually it didn't even work. I don't know what happened. Sorry. Okay. So moving on, we did part C, we graphed them both. Miranda looks at the graph and thinks something's wrong. So again, my apologies for lagging, but I did graph these. How many intersection points are there? If you notice, there was only one. Does this confirm your solution from part A? Explain your results. Well, let's look again at the graph. I'm going to try and look again at the graph. What is this point right here where they do cross? They cross at the point 3, 3, which means we're talking about x is 3. Going back to our original equation, does this confirm your solution from part A? Well, half of it. The lines cross when x equals 3. Okay, so let's talk about this. Why this happens, because this is going to happen in the future. When a result from a correctly solved equation does not make the original equation true, it's called an extraneous solution. We've talked about those in the past. It's not a solution of the equation, even though it's a result when you solve algebraically. If you've not already done so, check your solutions from part A of the problem algebraically. So if we look over here when we solved this problem on the left, we squared both sides of the equation to make it into a quadratic to solve, which gave us 2 answers. What we're now deciding is that this answer is good here, and this answer is extraneous. It's asking us to check our work, meaning we can plug them in. So if we try to do this and plug in our answers, if we do the square root of 2 times 3 plus 3, is that going to equal 3? The other one is the square root of 2 times -1 plus 3, is that going to equal -1? Trying to decide. Well, this is 6 plus 3, so it's the square root of 9. Is the square root of 9 equal to 3? Yes, 3 equals 3. On the right side, this would be 3 minus 2, meaning the square root of 1. Is the square root of 1 equal to -1? No, 1 is not equal to -1. So this is not a solution to the actual original equation, even though it appeared when we did some algebra. Just making another note. The fact that I'm going to read question 26, extraneous solutions can arise after solving correctly makes checking your solutions especially important. But why does the extraneous solution appear in the problem? Examine the graph of the system of equations y equals the square root of 2x plus 3 and y equals x shown at the right. Where would an extraneous solution appear on the graph? Why do the graphs not intersect at that point? Explain. Okay, we're going to look at this 2 ways. One of them, well, we're going to go back to Desmos and look there. So if we see this equation up here and we've got half, it's like half of a parabola. If we wanted to actually make it into a quadrat, like a parabola on its side, we could actually make and flip it over and make a negative square root of 2x plus 3. If you add that piece to the graph, you might actually notice that that is the other intersection point, -1. So what kind of explains this is, when you talk about solving it and you're solving and turning a square root into a square, you're actually, in essence, turning the graph of a square root into an actual graph of a square, which would have 2 solutions. It's not a perfect explanation, but in this context, it's probably the best one. So if you imagine this little graph over here, if we had it imaginarily going, right, it would keep going this way. And right there would be the other imaginary intersection point at -1, -1. That's a really bad scale right there. Sorry. A square root graph is really just the positive half. It's always when you're plugging in numbers, you're only going to get the principal square root, which is a positive one. If you wanted, so the explanation again, if you wanted to have a square root graph that was that bottom half of a sleeping parabola, if you will, you would have to have the negative square root you're looking at. So, big theme here, paying attention to extraneous solutions when you're solving. If you're graphing by just typing in a graphing calculator, you will see the correct single solution. If you're solving with algebra, anytime you're solving a square root, you may end up with something extraneous. Here's a slightly different problem that's taking a pretty complicated equation here with two quadratics equal to each other. There's this one here on this side and that one here on the other side, and they're equal. And Gustav is working this out. Sounds like he takes off and his teammates examine his graphing calculator to just see one equation, which is this one. So a couple things going on. Where does that equation come from? Where are the solutions? How are we going to do this? We're going to start by solving with algebra. If you are solving this equation on the left with algebra, ideally, again, we want to get everything equal to a quadratic equal to 0. So we're going to take everything off of this side. Take off an x squared, take off a 4x, take off a 3, right, on both sides. That's all going to turn into nothing, and we have x squared plus x minus 6. Nicely, that's something that we can factor as well. That's going to be x plus 3, x minus 2 is 0, which means our solutions are going to be negative 3 and 2. So, where does Gustav get the equation y equals x squared plus x minus 6? Well, it's right here. It comes from when he is solving and getting everything to a single side. I, right there in my solution, have it equal to 0. If you're wondering how many solutions this equation will have, well, set it equal to 0 and solve, which is what we did right there. Okay, so if we graph it, right, you can see these solutions right here on the graph. They're both there, just the graph of y equals x squared plus x minus 6, two solutions. They are negative 3 and positive 2. If we're going to keep kind of extending this, how do you see the solutions of that big equation in the graph of this? What would we call these? They are the y-intercepts. Oh my gosh, no, they are the x-intercepts. So how do you see the solutions to the larger equation in that smaller equation? Well, they are the x-intercepts of the smaller equation. So one more step on this idea. Maya solves this equation by graphing a system and looking for the points of intersection. What equations do you think she uses? So here's a drawing of them already. The blue equation right there would be the one, if we're looking at this, the blue one actually has a smaller scale factor. So I'm going to say the blue one is x squared plus 4x plus 3. And the red one on this graph, if you see the colors, is 2x squared plus 5x minus 3. Looking for the points of intersection, we should be able to find them here and here. I know the scale of this graph is very difficult to see, so I'm going to open these up on a graphing calculator so we can see those as well. Let's see, I've got another graph here for us. This is number 27. So this is the graph of just x squared plus x minus 6 with two solutions, -3 and 2. If we graph the other two equations, which now are green and blue, I'm going to change this one to red just to match what we had before. If we look for where do these two graphs intersect, they actually intersect at the x values, -3 and +2. Same as we already saw. They intersect right here. This one is -3, and this intersection point is x equals 2. Do we include the y values in the answer to this system? I don't know if you were asking that question, but the answer is no. The reason we're not talking about any y values is the original equation right here is only in the variable x. So there are no y's that are needed in an answer to this problem. What does happen is there's two big options. One of them is in algebra, if you combine the two equations and you solve it, you get your solutions like on the left, which does match up with x-intercepts of a graph. Or if you split your two equations, the left and the right, to graph them separately, your solutions would be the intersection points. That's it for these ones here. You have some practice you can do in the textbook, chapter 3, section 3.1.2. There's 1, 2, 3, 4, 5, 6 problems to do there. In the parent guide, there is an example to read through, but there aren't really any similar practice problems here in the parent guide. It is important to do the math by hand and or to graph by hand here. That's one of the goals we're checking, so try not to just type in answers or photomath or Desmos it. Try and make sure you understand this by hand, but that is it for 312.